Welcome to the first session of topic number 2, kinematics, and the subtopics are rest and motion, types of motion, speed, velocity, acceleration, scalar and vector quantities, like and unlike parallel forces. Rest. The objects which do not change their position with respect to the surrounding are said to be in state of rest. For example, a book lying on a table is in state of rest. I am sitting right now, so I am sitting, I am not moving, or you can say that I am not changing, I am not going to change my position, so I am in the state of rest. So all the objects which do not change their position with respect to surrounding are said to be in state of rest. The objects which change their position with respect to surrounding are said to be in state of motion. A moving car, a man walking on a ground, all these examples are of the state of rest because the objects are moving. Have a look on an example here. The tree, the car, trees, all these objects are not moving. They are not changing their position. So all these objects are in the state of rest. On the other hand, here a man is kicking the ball, bird is flying. So all these are the examples of motion because all these objects are changing their position with respect to surrounding. We have three kinds of motion. To know more about it, have a look on our video. Rest and motion, both terms are relative to each other. How? Have a look on this picture. To the observer, the ball has the same horizontal velocity as the train. He is the observer, he is observing the train. This man is with the ball inside the train. To him, the ball and the man has the same velocity as the train have. Second example, for this man, which is who is in the train, he is in the state of rest because he is sitting or he is standing. But to the observer, he is in the state of motion because he is moving with the train. So to him, he is in the state of rest, but to the observer, he is in the state of motion. This proves that the rest and motion are relative to each other. Both of these terms are relative. The most important terms to know kinematics are speed, velocity, and acceleration. To understand their concept, have a look on a video.
Speed. Objective. To learn the concept of speed. Speed is an indication of how fast an object is moving. It is a scalar quantity that refers only to the magnitude, which means speed is something that's measurable on a scale which shows how large it is. Think about a moving car that is covering a distance of 5 miles in 30 minutes. We would say the car is moving at a speed of 10 miles per hour. A slow-moving object has a low speed, covering a smaller distance in a longer period of time. Imagine a second car that's moving faster, covering 20 miles in the same 30 minutes. The speed of our second car is 40 miles per hour. A fast-moving object has a high speed, covering a longer distance in a shorter period of time. A stationary object, in this case a parked car, is said to have zero speed. But how do we determine the average speed of a moving object? We can calculate it by using the equation. Average speed is equals to distance traveled divided by time elapsed. Summary. Speed indicates how fast an object is moving. Speed is calculated as distance divided by time.
We have seen previously that speed is the amount of distance covered in a given amount of time. It's nothing but distance covered over the time taken to cover that distance. Simply put, it tells us how fast an object moves. Also, if we know the speed and the time taken to cover a distance, we can easily find the distance covered. So if I tell you that I traveled at a speed of 50 meters per second for 1 minute, can you tell me how much distance I covered? I am sure you've come up with the answer. I have covered a total distance of 3,000 meters. But if I covered 3,000 meters from this point, am I here or over there? You had no clue as to which direction I headed off. This tells us something interesting. Speed offers only the magnitude, making it what we call in physics a scalar quantity. It doesn't specify the direction. It just tells us how much ground is covered in unit time, regardless of the direction traveled. Scalar quantities have only magnitude and do not specify direction. Do you remember the difference between distance and displacement? Distance just tells us the distance covered, but displacement is distance with direction. Say the distance between towns A and B is 20 kilometers. So if we take a 50-kilometer route from point A to B like this, then the distance covered is 50 kilometers and the displacement is 20 kilometers north of point A. So speed does not tell us the direction. Is there anything that tells us the speed along with direction? Yes, it's velocity, which can be written as lowercase v. Let's see how it differs from speed. What if I tell you that I traveled north at a speed of 50 meters per second for 1 minute? Would you be able to tell me where I landed up? Yes, you would know I have covered a total distance of 3,000 meters and landed up at this point. Velocity is speed with direction of motion. As such, Velocity is direction aware. So when you mention velocity, you must keep track of direction. Something like the car moved south at 55 miles per hour. If you do not mention the direction and just say the car moved at 55 miles per hour, you're not stating the velocity anymore. What you are stating is the speed. What do you think is the unit of measurement for velocity? The unit of measurement for velocity, just like speed, is meters per second. Now you might ask, why meters per second? The cars we drive indicate speed in miles per hour or kilometers per hour. So why is the unit for velocity meters per second? The established SI unit of measurement for velocity is meters per second. When we are in a stationary car that moves rapidly to gain speed, we get pushed back against our seat. And when brakes are applied, we get pushed ahead. Or when we take a sharp right turn, we're pushed towards the left. These are all situations where we are accelerating. We have all experienced this, whether in a car or a bus or while riding a motorbike. Simply put, when velocity changes, we have acceleration. I still haven't defined what acceleration is. I just told you that when velocity changes, there will be acceleration. Okay, let me give you two examples. In the first one, a car is traveling in a straight line at a constant speed of 80 kilometers an hour. And in the second one, a plane is traveling in a straight line at a constant speed of 1000 kilometers an hour. In which case do you think acceleration is involved? None. In both cases, the velocity is not changing at all. Hence, there will be no acceleration in either of the cases. Most people relate acceleration to high speed, and that's clearly not true. Acceleration will only exist when there is change in velocity. Do you remember what velocity is? It's speed with direction, and it's hence a vector quantity. Why is this important? Let's say a body moves from rest and reaches a velocity of 20 kilometers an hour in 5 seconds. Will acceleration be involved here? Yes, because the velocity is changing. It was 0 initially, and at the end of 5 seconds, it's 20 kilometers per hour. In another scenario, assume that a body is moving at 30 kilometers an hour, and then it moves right at 30 kilometers an hour and continues traveling at the same speed of 30 kilometers per hour. Will there be acceleration in this case? The answer is yes. As the direction is changing, the velocity will also change. The only thing constant in this example is speed, but the velocity changes as the direction changes. So this was the most important concept you had to know about acceleration. It will exist only when there is a change in velocity. But how is acceleration calculated? Acceleration is defined as the rate of change of velocity. In terms of a formula, acceleration can be written as change in velocity over the time taken. If the velocity of an object changes from an initial value of u to the final value of v in time t, then the acceleration a can be written as v minus u over t.
Scalar and vector quantities. Scalar quantity has only magnitude, or you can say that scalar quantities are those quantities which can be specified only by its magnitude. By knowing only its magnitude, we can specify the scalar quantities. For examples, length, area, volume, speed, mass, temperature. Let's talk about the length. If someone asks about you the length, you simply said that it's 5 meter, 6 meter, 7 meter or 8 meter. You don't need any direction to specify the length. Same goes for the temperature. We simply said that 55 degrees Celsius, 6 degrees Celsius, 23 degrees Celsius. We don't need direction to specify the temperature. So all these quantities which do not need direction for their specification are said to be scalar quantities. And on the other hand, vector quantities are those quantities which needs direction for their specification. For example, displacement, velocity, force. If we talk about the force, for example, force is 5 Newton, but it also needs direction for its specification. In which direction you are applying? Someone can ask you, in which direction you are applying a 5 Newton force. So it means that force needs direction as well as magnitude. 5 Newton, 5 is the magnitude, and if you are saying that in right direction, so the direction, you need direction to specify the force, it means it involves both the magnitude and the direction. So all these terms which need direction and magnitude for their specification are known as vector quantities, and those quantities which only need the magnitude, means numbers 5, 6, 7, 8, 9, 10, for their specification are called the scalar quantities. Like parallel forces, the forces whose line of action are parallel to each other and all of them act in the same direction. You can see that in this diagram, all the forces are acting in the same direction. So these are the this diagram is the example of like parallel forces. On the other hand, the forces whose line of action are parallel to each other but they act on the opposite direction. You can see the arrowheads. These are in the opposite direction. So it shows the example of unlike parallel forces. Thank you so much.